Dr. Mendit, we can't hear anything.
Can anyone else hear?
No, I can't.
Oh, there we go. Hello? Yeah, yeah. Okay, good. Thank you. Yes. So you have to give me feedback, otherwise I don't have a clue. And be aware, I can't see the chat, right? So it's only obvious when you're in this room that I can't see any chat while I'm doing the. So okay, that's good. As long as everyone can text a friend in the class, and we can have some kind of buddy system if I mess up. So statistical is Markovian statistics. I was just saying to the people in the class that everyone will get my handwritten notes anyway for this module, so you won't have missed out on anything. And then graph is fairly straightforward. We have a center chain, and then off that we have small branches of different monomers. So there's lots of different structural ways these things can be built within a copolymer.
Dr. Mavitt, the people online can't see anything.
Oh yeah, okay, good one. It's all right, thank you. Good, how about now?
Good enough. Thank
Good.
you.
And don't, if it doesn't work, speak up, right? Because it's probably easier for me to hear you than it is to see. So thank you, I appreciate that. So when we're talking about, so throughout this course, and certainly in the first section, we'll talk about how we're going to make the polymers, and we're also going to talk about the mechanical properties. You remember the pyramid that we talked about before, and which balanced out the different application of the properties. As we go along, you'll start to learn how we can manipulate those mechanical properties to suit a need. Now, it's obviously important to study the mechanical properties for the materials because they can have different applications. So one thing that we look at in more detail is the elastic modulus. So I'm going to define that for you. So the elastic modulus represents the stiffness of a material when the elastic range, within the elastic range when tensile or compressive load applies. So the mechanical properties are determining how well it will work or not work for a given device. And one major factor is this modulus that we've defined. So we know that there is a progression down for this elastic modulus, that metals are going to be a lot stronger than polymers, but there's different polymers that we can play around with and manipulate. And then they're stronger than the elastomers, which are in turn stronger than hydrogels as well. And that's why we're using hydrogels, right, to put as flexible polymers to put on the eye as contact lenses. So you can see that the modulus changes as you choose different materials. There's a few examples. I'm not going to read all these out. There's a few examples of different moduluses of materials in comparison to the cortical and the cancellous bone in the body there. So some of the important factors, or certainly mechanical properties of biomaterials, is that we don't want them to permanently deform or fracture under physiological loads. And the mechanical properties can change the host response and device success. So you may have come across this before. I think most people that have done this class have come across stress shielding and Restenosis stress shielding is when you kind of have a blown implant, and then your bone is not given time to remodel because the actual implant is taking more of the stress than the surrounding bone, so it doesn't regenerate as quickly. Restenosis is a cardiovascular condition when you put a stent in that actually it actually forms a thicker endothelial wall and actually can cause a collapse of the arteries as well, because it basically takes on too much load than it should, so it doesn't have time to reform. So the load really depends on the device. Obviously, if we're having an implant in the leg, that's going to take more load than an artery load. So that's important for defining the properties of the material they need, and obviously modulus is in there. So the modulus will be dependent on the material's ability, the material structure, composition, the defects and the impurities in there. So this is just an example. This is it looks like an acetibular cut there that's deformed. So you can see that the outside brim over time has started to wear on those things, and that's because the modulus is not matched up to the area that's going to be taking the load, right? So this is an example of it's actually a bone plate that is put in there. The bone plate consists of stainless steel. So you can see that is much stronger than the cortical bone. The higher modulus of the bone plate versus the surrounding tissue causes this stress shielding and leads to bone loss. And that results in the implant becoming loose and then possible fracture and loss there. So I think this is pretty heavily studied, so I'm not going to go into it too detail. We actually assess it a little bit later on in more detail. And then this is the example of PLLA, the polymer PLLA uses a bone plate. So you can see that is much lower elastic modulus than the cortical bone. It means that it's about 8 times less. But you can see that because it can't take on, because it's not as strong, you can only use it in low load bearing applications, right? It's not going to be supporting the femur or anything like that. It needs to be in wrist applications, or kind of a lot of spinal bits use it as well. And then restenosis, again, you can see that the stainless steel stent that they use has a much higher elastic modulus than the artery itself. And that actually causes this reblocking of the artery due to the formation of a neo-intima, which is a thick, smooth muscle tissue inside that lumen there. So we'll come back to those a little bit later on. There's a section on orthopedics, and then there's also a section on cardiovascular disease, which is, I think it's actually module 15 right at the end there. So I'm not going to spend too much time on that. Now, one of the cool things is, and this is where there's a lot of application in the polymeric biomaterials, is biodegradable polymer stents. So most of you have probably seen these as arterial implants to hold open those arteries. You can use biodegradable polymers in there. So what happens is they're long enough to allow the artery to remodel, and then it starts to dissolve. But some of you will be taking the drug delivery class. You can use it for the drug delivery applications, right? And then you'll start to discover, we do a little bit again later on in this course where we talk about the different modes of dissolving these polymers down. But this minimizes the restenosis, and you can see the modules are a lot closer between the PLA stent and the artery. But the disadvantage to that is that it can collapse, right? Because it's not as strong. So there is a balancing out of those things. That is why structurally they build it to look like it is, right? Look to help support it and give it strength. So then we also have polymers in ophthalmics. So we're looking at using intraocular lenses there, so you can replace these cataracts using like a polymeric material. So back in the day, I think there was a lot more PMMA. Actually, you used to put glass I mean, I wear contact lenses. I'm not sure how confident I would feel placing glass directly into my eye, but that is how it used to be. Then they moved to PMMA. PMMA is relatively inflexible. It's rigid, but in their replacement, they needed a larger incision. So that's now why they go to the silicone acrylates. So they're much more flexible, much more foldable. It means when you're doing a replacement, you need a much smaller incision in the eye there. And they're done for a mixture of the PDMS and PMMA, but they get a good flexibility there. Much lower TG, which we'll come to in lecture 3 or 4. So you'll see the importance of those on that structure as well. So that's it for this. So that's the introduction done. So we've made some good headway there. So now I'm going to switch over to my other. Yeah, that's a quick transition. So now we're going to have a look at some of the polymer classification. We're going to talk a little bit more about stepwise chain addition, condensation, whatever you want to talk it, whatever you want to call it. Let me just get this. So we're going to talk about some of the naming systems that we have here. So really simply, the source, we can use source or structural naming systems. The source naming systems are based on the monomer name. So we can take something, for example, like styrene. I would say that in the exams as well, I never really test the name of the monomers and the polymers, but I think it is a useful tool for you to know later on. Certainly, if you can remember, you can relate that to the structure really easy. I think that's a good thing to start to comprehend. But you'll see things such as styrene crop up and polystyrene crop up quite a few times because it's an interesting polymer. So when we get styrene and we undergo polymerization, does anyone know what method of polymerization that would undergo? Yes, yes, yes. Double bond, got it. So it's addition. Just because of that double bond there. And then we just draw it as the polymer form. So that's the polymer form of it. Get used to that because you're going to have to draw some of those things out. So I don't mind if you do square or round brackets. I think I've said this before. It's perfectly fine, but you have to remember to put the end there and make sure that your bonds stretch outside that bracket to show that it's continuous. Now there is another way of drawing this. This is the more usual way of doing it, but you can also draw it in, I suppose it's kind of chemistry shorthand. I've done this class several times now and I can still never draw the phenyl ring perfectly. It looks about right. So that's the shorthand version. So again, it's perfectly okay if you want to go for the shorthand version in the exams as well. Let's not forget the end. So the repeat unit is also called the monomeric unit. I'll give you a second to get that down. Now, the interesting thing is that polymers that are made from the same repeat unit structure can have different source names due to them being from different sources. So polymers with the same repeat unit structure can have different sources names due to being from different sources. So one example of this is ethylene glycol. Ethylene glycol is not ethylene glycol, but the precursor to the polymer, which is polyethylene glycol, polyethylene oxide, assumes either a straight chain, the monomer is either straight chain or cyclic. So you can do a ring opening polymerization for this one. But the straight chain version is like this. A lot of you have seen or probably come into contact with PEG, certainly if you work in some of the undergraduate research labs. So PEG is actually more prevalent than the next one we'll draw. So you can see it's called polyethylene glycol because the monomeric units are called ethylene glycol. Now for the cyclic structure, you have ethylene oxide. And when we do the ring opening polymerization, we actually get the same structure or the same polymer. But we actually just call it polyethylene oxide, PEO. So really, depending on what the polymer name is, we know what the starting material is, and that's really the take-home message of this slide. So PEO is normally more prevalent in polymer chemistry, and it's generally higher molecular weight. We also have a similar problem for what we call PGA, which can be a polyglycolic acid or polyglycolide. So the acid form of that, which is a straight chain, would look like this. And you will notice this one has got functional groups on it. Therefore, if it's got functional groups on it, it has to proceed by a condensation reaction. There is a few which are in between the addition and condensation. We'll explain what those are. Some actually don't lose any small byproducts of it. But now you can see there's no double bonds in this one. It's just a straightforward acid and an alcohol on each side. It has to proceed by a condensation reaction. I know it seems simple sometimes, but that's where a lot of people get caught up. But then the glycolide version is the cyclic version. I don't know whether it's my accent sometimes. I say cyclic. You say cyclic. Some people say cyclic. Okay, good. So you can see that the end naming is defined by the monomer that we used. So then there is linkage-based names in there. So we're really talking about the structural group, the functional groups coming together to form a linkage, or in the case of polystyrene, the linkage in polystyrene between the polymers would be just a vinyl, what we call a vinyl linkage. So the backbone is CC, we call it a polyvinyl. So again, there's lots of different terminologies for what vinyl, unsaturated, saturated, and they're used interchangeably. So just know that if you read those things in books, then you come across different variations. So polyethylene oxide, or PEG, that you saw before, as a COC. That is actually an ether. So the linkage name would be polyether. And then the glycolic acid, the linkage for the glycolic acid, I'm not going to draw it all the way out, but the linkage would be this linkage here. That linkage there is an ester. So it would be called a polyester. And these are like giant classifications, right? Under that, there would be sub-classifications of these polymers, but everyone's heard of polyesters, maybe not so much polyethers, maybe polyamides. So they're kind of big families of polymers in there. So there is also end groups in there. End groups generally are not, we don't use them in the naming terminology. They're often excluded from the repeat structure as well, if they're not important or reactive. So typical end groups could be something like a thiol. And again, you'll see this a bit later on. Thiol modifications are really important for adhering things to surfaces. So what you would essentially say there is that, you know, polymer is thiol terminated, and make sure that if you were writing a publication on this, people knew that that thiol modification was integral in adhering things to the surface. Sorry, that's a surface modification. So polymers containing reactive end groups capable of contributing to further polymerization or chain extensions are called, I can never pronounce this, telecalic clause. I'm going to spell it out. So you can see on the bottom here, this is actually, I think this is an image directly out of the book recommended on the syllabus, but these different telecalic claws are really these branches that come off, and they're capable of extension and further reaction to extend those polymers. So things such as OH, hydroxyl groups become important there. Now, the next definition is based on structure. So that's how many types of monomers that we use, or the numbers of, or different repeat units in there. So we've already said before that the homopolymer is prepared from a single monomer type. It's a polymer with one type of repeat unit in there. So some examples here will be PGA. Should just be A, so on. And then PLA. The only real difference between PLA and PGA is that you've got this methyl group on the bottom here. That's B, 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 B. So that's fairly straightforward. And then copolymers are prepared with 2 or more monomers. And it's a polymer with 2+ types of repeat units. So what we actually use for these is a zigzag line between the connecting 2 repeat units to indicate that the sequence and order is not known. So the zigzag line is almost like an unknown that we don't know, but we know that that copolymer is in there. So it's repeat unit, sequence, order is not known. So we might draw it something like this. We can take our PGA. I should have warned you this lecture has got a lot of writing in this one. Notice I used an N and an M there, just to show that it's different units. That makes it easier to report if you're, writing a publication on these things. Is that if you say that M varies by this number of repeat degree of polymerization or this many monomers, then they know what you're talking about, rather than just having 2 N's, one for the PGA and one for the PLA. So this actually would be called copolyglycolic acid, lactic acid. So that would be the terminology for that one. So then we can start, you've seen this before, but we can start to add kind of subunits or sub-expressions to different copolymers to explain how the monomers are distributed within that polymer. So if we just use expressions A and B, we've got 2 different monomers. Random would be something A, B, completely random. And that would be called RAN, copoly A/B. Alternating, you can probably guess, is just A, B, bless you. And that can be alt copoly AB. And then we can have block A, B, B, B. And then we would call that block copoly A. Hopefully you're getting this now. All right, it's fairly straightforward. And then the graft is just A, where we have the single backbone there, and then we can have B coming off it. So that would be graft copoly A, B. So you can shout out at home or in the class. What would that second one be called that I've drawn out? I can still hear you at home.
Draft copoly BA.
Exactly, yeah, easy. So the main body of the main backbone of it always comes first. So that's good. Graft, copoly, BA. Oh, I've put it underneath anyway, right? So if you read on this, what it says that. So the first name is given to the polymer backbone, and the second name is given to the graft. So I'm gonna. The next one is actually an in-class problem, but what I'm gonna do is I'm gonna give you a little bit of time from now till the end of the lecture to start going through some of those problems and see if you can come up with naming systems for them. I would say that the error on this page is that octo acrylate is actually O. So have a go from now till the end to do those, and then when we return for the next lecture, I'll have the answers up there for you. Okay. I have office hours today as well. It's between 12 and 1. So if there is an issue, please reach out. Okay. So it seems like today Zoom is having some issues. I don't think the first issue, I think that was an issue with me not having it set up right, but there is some issues with Zoom. So if you're struggling to get access or was struggling to get access, they're trying to remedy that. So has anyone got the answer to the first one yet? Still working on it.
Ran copoly OM.
Yeah, good. About the second one. Yeah, block copoly OM. third one. Yeah, graft copoly OE. Now, the last two are the most difficult ones for sure. And actually, I've done this class several times. I think people write this the right way, but there's several variations of the right way for it. Let me start writing these ones in. So that's ran copoly. Say that again, sorry. Yes, so that is, yeah, I think that's it. So it's block copoly O, and then graft copoly MA. ME, right? ME. So I think that's it for now. And then what we'll do is next lecture, I'll finish filling off all these in, and hopefully we'll get to the end of this, and we'll start moving on to having a look how we get some of the structural features of polymers that bring about the properties, and how we get those polymers into solution to make measurements on them. Okay, good. It's a good turnout today. No, I'll write that one down for you. There's about 4 different versions. It'll probably take me 45 minutes to write it down. Yeah, okay. So that's it. So I have office hours today. Well, so I'm undecided on that. So this week I have to get the people that have been here. I have to get you registered in Howdy and say that you've been here. But actually, I can track your registration if you've been using remote. I know there's some people in the class that have attended all the classes, but I can find out if you've been here or not. Right. So, but I might do next lecture. I might actually just try that Google form and see what happens. It's a bit of an experiment sometimes, these things, but we'll find out something that works. And I'm also conscious that we need to find out something that works for in-class problems as well, so the people at home can integrate with here. And it feels a bit weird speaking into, everyone's watching, but speaking into space, asking people remotely if they've got the questions. Okay. That's good. So yeah, any more questions, let me know. And like I say, I've got office hours today at 12 till 1. So if you have any issues, hop on along. Links in the syllabus, by the way, for that.